Hi everyone, thank you for joining today's virtual meeting. Today we have our honorable guest, Dr. Jennifer A. Lowe. She is a postdoctoral researcher in Sandia National Laboratories. So she will first talk about, give a technical talk about GMRES linear solver. Then it has two parts. This talk has two parts. In every part you'll be able to ask questions. First you can ask questions about her talk, and then she will show about her journey in career in national lab and how is it to work there. And there also you get a chance to ask questions. So Dr. Jennifer, you can proceed.
Thank you so much. Well, thank you for inviting me. It looks like my cat may try to join this presentation also, so we'll hope he doesn't get too disruptive. So I'll be talking about my research first in incorporating multiple compute precisions into the GMRES linear solver. And then the second part of my talk will be about working at a national lab. And this is a really small group, so feel free to interrupt me at any point with questions. I don't think I can see if you raise your hand, but if you just unmute your mics, I should be able to hear any questions that you have. Okay, so in PowerPoint here, a little bit of background about me. I earned my bachelor's degree from Oklahoma Christian University. I had a mathematics major with minors in computer science and international studies. After a little bit of switching, I started as a math computer science combined major and then decided that I really liked proofs. So I switched to a math major with a computer science minor. I got my master's and PhD in mathematics from Baylor University. And now I'm a postdoc at Sandia National Laboratories in the Scalable Algorithms Department in what's called the Center for Computing Research. I study numerical analysis, which if you're not familiar with that is essentially how do computers do math. I focus on numerical linear algebra. So in particular, I'm usually working at solving linear systems and eigenvalue problems. And I specialize in Krylov Subspace Methods. So who needs to solve such linear systems? Anyone modeling physical phenomenon with partial differential equations, which we have quite a few people at the national labs using such PDEs. So these PDE discretizations are typically using finite elements or finite differences. And the matrices can be very, very large. So N is often much bigger than 1 million. And these matrices are very sparse, sparse meaning mostly zeros, and often they have less than 1% non-zero elements. The diagram I have on the right is a picture from the ExoWind project. You can look that up. It's a project to simulate airflow around wind turbines or a whole entire field of wind turbines. And this particular problem that results from the picture on the right has 95 million unknowns to be solved for. So what makes it numerical linear algebra? What things am I particularly looking for in my research? The numerical piece refers to calculations as done by computers. And remember with computers, I don't know how many of you in the room work in numerical analysis, so I'll start from the beginning. Computers don't work exactly like your exact proofs in your typical linear algebra class. Computers have memory requirements that we have to take into account, especially with matrices that have size 95 million. We have to take into account computational cost. How long is it going to take to solve this problem? We need to consider conditioning and stability. We don't want to propagate any round-off error, and round-off error can significantly propagate in numerical algorithms. And we need to form algorithms for parallel computing because most of our computers nowadays are parallel. So looking at my research in multi-precision GMRES, my main research question is, how can we take advantage of lower precision data storage to speed up linear solvers? Or in particular, how can we use it for the Krylov solver GMRES? Now, if you're not familiar with Krylov methods, I'll hit on the big ideas here. So for these large sparse matrices, these problems that we're working with in the national labs, we can't use direct methods such as Gaussian elimination. These are simply too expensive for the large problems that we're working on in real life modeling. So we use an iterative method. In particular, we use a Krylov method. And the big idea with the Krylov method is when we're solving the linear system AX equals B, we want to pick a good small subspace of Rn in which to search for a solution, and then we want to find the best solution in some sense from that subspace. And for Krylov methods, at each iteration, we expand the search space by one more basis vector to get a better solution. Okay, so going a little bit more into the details for GMRES, GMRES stands for the Generalized Minimum Residual Method. It's a general Krylov method for any non-symmetric linear system. You can use it for symmetric linear systems, but if your system is symmetric, positive, definite, you probably want to use a conjugate gradient method. The GMRES method is good for any linear system. And first, to get our small subspace in Rn, we're building an orthonormal basis for a Krylov subspace. Now, a Krylov subspace is just a fancy word for a multiply by a subspace. So we'll start our subspace with the right-hand side vector b, normalized to have norm 1. And then the next vector, we use a times b, and then a squared times b, and so on and so forth. Whoops. And each time we form that next matrix, that next vector for our subspace by performing a matrix vector product. We don't ever want to compute the matrix a squared and a cubed and a to the fourth and store that entire matrix because our matrix is too large to really hold that in memory. So after we've computed our Krylov subspace and we've built an orthonormal basis, we can use an orthogonal projection to find an approximate solution which minimizes the residual b minus ax hat. And this is the residual in the 2 norm in this case. And for physics problems, typically we're looking for an accuracy of about 10 to the negative 8. Okay, so here's the full GMRES algorithm. You don't need to follow all the pieces of this, but just to highlight a few. At the beginning, we take that right-hand side vector and normalize it. And then in this main loop from lines 2 to line 10, first we do a sparse matrix vector product to get the next basis vector in our Krylov subspace. Lines 4 through 9 are orthogonalizing that basis vector against the previous vectors in the Krylov subspace. And then we rinse and repeat, going back to step 3, doing another matrix vector product, orthogonalizing that vector against the previous vectors, and so on and so forth, until you've taken enough steps. And then in steps 11, 12, and 13, we define our small projected problem to get our approximate solution. That small projected problem with a least square solution in line 12. And then in 13, we found our approximate solution. So you'll check the residual to see if it's at the tolerance you want for convergence. And if it isn't, then you can continue adding vectors to the Krylov subspace and make a bigger subspace and continue on. Okay, so computers and precision. I don't know how many of you have a computing background, but remember that on computers, numbers are stored in binary, so zeros and ones. And each binary digit is called a bit. Double precision numbers are typically what we use when we're working on computers, and those are stored with 64 bits. Single precision numbers are stored with 32 bits. Half precision numbers are stored with 16 bits. And each of these sets of bits is split into a sign bit, an exponent, and a significand. These numbers are all written in exponential notation in some sense, and you can look that up if you want more details. So in particular, here's what the number pi looks like in each precision level. Okay, so you've got double precision on the top with your 64 bits. That 0 in the orange in the front is your sign bit. The next several bits in the yellow are your exponent, and the rest of it is the significand. And then in single precision, we still have a sign bit, a few less numbers for the exponent, and then less numbers for the significand, and then half precision. Okay, so why would I want to store numbers in a lower precision? Why not just keep everything in double precision? Because that's going to be more accurate, right? Well, most modern computer algorithms are what we call memory bound. So by memory bound, I mean that throwing a faster computer processor at the problem isn't actually going to help anything. Okay, so you may remember with your laptop, sometimes things get slow because you have to read a big file off of your hard drive into RAM. And sometimes your computer can even completely freeze up because you've gotten, 15 Google Chrome tabs open and your RAM is filled up and your computer is thrashing, can't use that memory very effectively. Well, actually, beyond your hard disk and your main memory, there are other levels of memory that a program has to go through in the hierarchy. Let me see if I can get a pointer here. There we go. Okay, so after we've read the main problem off of the hard disk and it's sitting in RAM, before it gets to the CPU, before we can perform any computations with it, sparse matrix vector products or orthogonalization with our Krylov algorithm, the data has to move from main memory, the RAM, to the L3 cache, to the L2 cache, to the level 1 cache, and the level 1 cache sits right next to the CPU. So any data that we want to move, that we want to do calculations on, has to move through all of these levels of cache. As stated in the diagram, the levels of cache get smaller and smaller and smaller as you get closer to the CPU. And so what actually takes the most time in these algorithms is moving data between different levels of cache. A faster CPU isn't going to help the algorithms go any faster. So the idea behind using lower precision is that using lower precision data means less data movement to be moving through all of these levels of cache to the CPU. And perhaps we can get rid of some of the memory movement cost in our algorithm. Okay, so here's a diagram. Let me direct your attention at first to just the green line and the blue lines. Let's compare double precision GMRES versus single precision GMRES. So I have a matrix here that's a 2D convection diffusion problem, which means it's highly non-symmetric. N is about 2.25 million. On the y-axis, we have the norm of the residual, which is the norm of the right-hand side B minus A times X hat, our approximate solution. And on the x-axis, I'm counting the number of iterations that I'm using until convergence of my GMRES linear solver. And this is actually for GMRES 50. The 50 means that I'm restarting the GMRES iteration after every 50 basis vectors that I add to my Krylov subspace. So for this problem, the double precision GMRES converges in almost 13,000 iterations, which is quite a long time for GMRES. Normally we would add a preconditioner there. And it converges to a tolerance of 10 to the negative 10, which is what I've asked for in all the experimental problems you'll see later. Well, the single precision GMRES, we wish we could just simplify everything and do everything in single precision, but we only get an accuracy of around 10 to the negative 5. So 10 to the negative 5 isn't good enough of an accuracy level for the physics problems that we're trying to solve. So we need more accuracy, but we don't want to run the entire computation in double precision, but we can't run it all in single precision. So what can we do? And it turns out that one way to combine precisions and use more single precision in your solver is to use iterative refinement. Okay, so the algorithm below is an iterative refinement scheme with GMRES error correction. So what I'm doing is I'm computing my residual in double precision on line 1. And then on line 3, I'm running GMRES in single precision for so many steps. I think every piece of my computations ran GMRES in single precision for 50 steps. And then after 50 steps of GMRES, at the time where I would normally restart the solver, I compute my new solution in double precision. I compute my new residuals in double precision. And then I use that new residual to restart GMRES. I use this new residual as a new right-hand side vector for GMRES, the new starting vector for my Krylov subspace. So updating these residuals in double precision takes the rest of the error from the original problem and uses that in the single precision GMRES to help solve your final system. So again, I'm computing residuals in double precision, running GMRES, running that error correction piece in single precision, and then I'm computing residuals in double precision again. And we'll keep running this until we get convergence. Okay, so here's the same graph we were looking at earlier. Remember, the green line is GMRES convergence in double precision. The blue line is GMRES convergence in single precision. And now we can pay attention to the red line, which is the convergence of GMRES with iterative refinement. And so we were very happy to find that in many, many cases, the convergence of this GMRES with iterative refinement, GMRES IR, very closely follows the convergence of GMRES double. So if you think about the algorithm here, we're doing quite a bit of the work now in single precision. All of the GMRES iteration, these matrix vector products, and this orthogonalization is being run in single precision. And the only thing we're doing in double precision is a few residual computations. Okay, so doing the bulk of the work in single precision with the red line, only doing those residual refinements in double precision, and we get convergence following the residual curve of the GMRES double precision solver. And this was really exciting. So comparing the solve time, you'll notice that the double precision GMRES took 50 seconds to converge, and the GMRES with iterative refinement took about 38 seconds to converge, which is a reasonable speed up. In this next slide, I'll break down that speed up even more. So remember from our previous slide that the two main expenses in running GMRES are the sparse matrix vector product and the orthogonalization. And so in the diagram here, the purple portion near the top of the bar represents the cost for the sparse matrix vector product. We've got double precision GMRES on the left and GMRES with iterative refinement on the right. The y-axis represents your total solve time in seconds. And the purple portion of that bar, the second from the top, is the portion of time spent in the sparse matrix vector product. The three sections below that, the green with the GMV, which is a matrix vector product, and the blue with a GMV transposed, another matrix vector product. The orange represents a norm. Those three sections are all of the main costs of the orthogonalization. So you can actually see that here in this instance, the orthogonalization takes up the bulk of the time for the double precision solver and the iterative refinement solver. And in the table below, these three lines here talk about the time of the orthogonalization, and we get some pretty good speedups. With the GMV transpose, we get about 0.28 times speedup, but with the GMV without transpose, we get about 1.57 times speedup, and a little bit of speedup in that norm section. Overall, we get about 1.32 times speedup, so going from 50 seconds to 38 seconds. And in the sparse matrix vector product, we get a 2.5 times speedup, which was really interesting to us. That GMRES and double went from going 7.33 seconds for those sparse matrix vector products to 2.95 seconds in GMRES IR. And GMRES IR was doing a few more sparse matrix vector products. So why did we get more than double the speed up? I mean, going from double precision to single precision, you would think that you're storing half the data, so you would at most get 2 times speed up. And there's a somewhat complicated explanation for that, but the short version is that when you convert your data into single precision, we have better caching. So that diagram that I showed earlier, the L2 cache is better used. The right-hand side vector for the sparse matrix vector product in single precision actually fits into the L2 cache, while in double precision, we need to keep rereading components of that right-hand side vector. So this improved caching is what gives us 2.5 times speed up in the sparse matrix vector product. So here's a larger set of results for a set of test matrices from the Sweet Sparse collection. These three here were done with polynomial preconditioning, if you're familiar with preconditioning at all. This column represents the size of the matrix. Here we have the solve time for double precision GMRES and the iteration count. And then over here is the solve time for GMRES with iterative refinement and the iteration count. Here I have the speedups in the very last column. The more green the number is, the higher the speedup. So with this Laplacian here at the bottom, we had 1.44 times speedup. And several of the matrices we tested did get close to that 1.3 times speedup we saw with our example problem. Now, there are a few of them that had slowdown. One of them here for stomach, I think the problem is that it didn't need very many iterations. So we talked about how GMRES with iterative refinement usually needs a few more iterations than GMRES double, and it does. And since GMRES double only took half a second to converge in the first place, GMRES IR couldn't quite make up for that with its 40 extra iterations that it needed. So GMRES IR gets a little bit of slowdown here. This parabolic FEM was interesting. It was one of the exceptions to the slide that I showed you earlier. This is one case where the GMRES convergence with double precision doesn't quite follow with the GMRES convergence with the iterative refinement. The iterative refinement needs quite a few more iterations to converge. So we have 36,600 iterations over the 27,000 iterations. That's far more than just a few extra iterations that GMRES IR typically needs to catch up. So we need to investigate why the convergence of this particular problem didn't work as well with the iterative refinement. But overall, we're getting reasonably good results. So our future work is to implement this GMRES with iterative refinement solver into the T-Petra solvers section of the Baylor package in Trilinos. So Trilinos is one of the big solver packages that comes from Sandia. You may have heard of PETSI. That's a similar package that comes out of Argonne National Lab. The software that comes from Sandia Labs is called Trilinos. And the Baylor is the package for linear solvers. Trilinos also has several packages for PDE discretizations, multi-grid preconditioning, ILU preconditioning, all sorts of solvers, and different mathematical routines. So we're trying to code that up and contribute it to Trilinos. We'd like to test GMRES IR, GMRES with iterative refinement on some real-life applications. So one in particular we've been looking at is an ice sheet modeling problem, and we're trying to work with that team to see if this technique can get some speed up on their linear systems. I haven't talked much about half precision today. We're only just now starting our investigations with half precision, but we might look at incorporating half precision into our linear solvers. And the tests that I showed you today were run with an NVIDIA V100 GPU, but we also need to test performance of this solver on other GPU architectures, specifically AMD GPUs and Intel GPUs, because two of our newest supercomputers that are going to come out in about the next year are going to be using AMD GPUs and Intel GPUs. So thank you for listening to the research portion of my talk. Do we have any questions at this point?
I think nobody has any questions.
Actually, I do have a question.
Okay, great.
Thank you very much for giving us this nice talk. I really appreciate that. So I do have a few questions because you know that we are in the math department, so probably not so familiar with the computer science. Could you please explain a little bit further about what is, for example, half precision? I kind of like understand what is double, what is like single, but then what does it mean by half precision? And I would like to also ask another question is on page 13, when you're describing this iterative refinement, I think you have like basically 4 steps, and in one of the steps you are using single precision, right? And then all the other steps you are using double. Could you please explain a little bit further why you are choosing this like one particular step to replace it from single but not the others?
Sure, those are really good questions.
Thank you.
Okay, so again, looking back at this slide, I talked mostly about the double precision with 64 bits and single precision with 32 bits. Half precision uses half the number of bits of single precision. Okay, so you can see here how we've stored the number pi at each level. And if you were to look this up on Google or YouTube, you can actually see some detailed explanations about how they convert your base 10 number into the binary number with all of these different pieces. But the main idea to remember is we're using half the storage of single precision with this half precision. Now, as for why did I choose this particular step? Let me make a quick clarification here. So step 3, when I'm saying use GMRES M, these steps 1, 4, and 5 are all really simple operations. I can code each of lines 1, 4, and 5, each of those with the red boxes, in one line of computer code. This step 3 is the entire GMRES algorithm. So what's in step 3 that I'm doing in single precision is, where did I put GMRES? Is this entire algorithm that I've got right here. So step 3 that I'm running in single precision, it's really all of this stuff that's being run in single precision. And basically the idea was, how can we get as much of our computation as single precision as possible? And we know that this step 3 with the sparse matrix vector product, those are pretty expensive. And this block here with the orthogonalization, that's pretty expensive. So if you look at my graph closer to the end, okay, so with the double precision solver, the purple box is the sparse matrix vector product. These other 3 boxes are that orthogonalization kernel. And so that's the bulk of the expense of the algorithm, right? So by taking these sections, and converting them to single precision, we've taken all of the most expensive sections of the algorithm and we're starting to run them in single precision. And so when we compute those extra residuals in double precision, the only thing that adds to the solve time is that this gray section gets bigger. So this gray section is that little bit of small computations to compute your approximate solution in double precision. And in the iterative refinement box, I've added in the time to compute the residuals. We've only expanded that gray section from maybe 2 seconds to 5 or 6 seconds. Actually, 2 seconds to 4 seconds. But we've crunched down the time for all of these expensive operations. Does that answer your question?
Yeah, that definitely makes everything clear. Thank you very much again.
Thanks for your question. Any further questions?
Can you hear me?
Mm-hmm.
So what inspired you to, to make some change of the double positions or single instead of, algorithms, but how we apply the algorithms?
So you're saying why mess with the precision of the algorithm instead of messing with the mathematics of the algorithm?
Yeah, I mean, that's really smart. You think about like, if I can do the double precision or single, so it can improve the computational time or the, that's really smart. So I want to know, like, how do you come up with this? You can do something on the, the positions.
Mm-hmm. So that's a good question. And there's really two pieces for it. The first piece is that I work at a national lab, and you don't always have 100% freedom to choose what you research at a national lab. So I came into my postdoc position, and my mentors said, hi, we have funding to work on multi-precision algorithms. You do linear solvers, we're going to work on multi-precision linear solvers. Go do something with multi-precision linear solvers. So that was part one, is just there's this big initiative going on right now in the Department of Energy and in several other places to investigate multi-precision algorithms, and our lab decided they needed to be a part of it. So this is part of what we're doing. Now, a more practical answer as to why wouldn't you look at something more algorithmic to improve the algorithm wise rather than looking at multiple precisions, we should be looking at other versions of improving the algorithm. We've looked at communication avoiding algorithms, or with linear solvers, we really should be looking at good preconditioners. And we have several people at Sandia looking at that as well. But I think at the end of the day, you remember at the beginning when I said that most linear solvers and computational algorithms are memory bound. So it's not a problem of how fast the computer processor goes, but we're spending all of our time moving our data between different levels of the memory hierarchy. I think even if you came up with a different algorithm, it would still probably be memory bound, because that's just the state of our modern computers today, is that nearly all of our mathematical algorithms are memory bound. So you could come up with a better algorithm, and that would be great, but you're probably not going to address the memory issue until you start looking at lower precisions.
Oh, thank you. That's really nice. Like if you have algorithm and you apply the, the double and single precisions, and you can improve the algorithm, like improve the overall computational time. Mm-hmm. Also, you mentioned that L2 cache. How do you know that for the single for the single position, so it, it doesn't need to make any change, so it can, you mentioned that it's the data passing through like different stages. Mm-hmm. How do you observe it's because of L2 cache?
So for that, I had to go into the NVIDIA profiling tools. So I was using an NVIDIA GPU. If you're not familiar with GPUs, GPU is a graphics processing unit. So just a few big ideas with parallel computing. When you're working with a normal CPU, a CPU probably has multiple cores, like probably your laptop at this point has 4 cores. And those 4 cores are each pretty smart, and you can give them completely independent tasks. One of them could be running your web browser. One of them could be running MATLAB for you. One of them could be running your LaTeX compilation for your thesis, so on and so forth. Those cores are really good at being independent, but there's only a few of them. So on your laptop, there's probably 4 cores. On a supercomputer node, you've probably got anywhere from 16 to 40 cores that are really good individual workers and independent. On a GPU, on a graphics processing unit, these were originally meant for graphics processing. So think, video games, something where maybe you need to do the same thing to each pixel in a picture over and over and over. So GPUs have thousands and thousands and thousands of cores, but think of a CPU as being really smart. Your cores in your laptop are really smart, and a GPU is like a big collection of dumb robots. So your GPU has lots and lots and lots of workers, but they can't work independently. Each set of 32 workers has to be doing the same thing at the same time. So you have to be careful of what operations you give to a GPU. So dense linear algebra operations, like a dense matrix times a dense matrix, run pretty well on a GPU because you can tell the same workers you're doing the same thing, do a multiplication and an addition. But other complex operations don't work as well on a GPU. Okay, so that said, how did I figure out that we had this 2.5 times speedup and how we were using the L2 cache? So I can go into the NVIDIA profiling software for the GPU, and I ran some profiling of, what does the matrix vector product look like in single precision? What does it look like in double precision? Test some different sorts of matrices. And my background isn't really in computing either. So at this point, I had to go get my friends from the COCOS team who are really good with everything GPU. They're all computer science guys. And I said, look at these profiling results. What do they tell you? And they were able to explain to me, look at this cache hit rate. The hit rate for a cache is basically when we look in the cache for the data we need, how often is the data that we need already there? So basically, if you looked in your office for a library book that you need, how often is the library book already in your office versus having to go fetch it from the library? And the L2 cache hit rate went up significantly for the single precision right-hand side vector for the sparse matrix vector product. And so with my friends on the COCOS team who know lots more about GPU computing, we were able to come up with a model that showed exactly why we were getting this 2.5 times speed up. So that was really interesting.
Thank you. And you made a really good slides and presentation.
Thank you. Okay, are we ready to go on to the next section?
Yes, we are ready.
Okay. Okay, so part 2, I'm going to talk about what it's like to work at a national lab. Here we go. So of the national labs, there are 17 national labs from the Department of Energy at the United States. 16 of these are government owned and contractor operated, which means that my workplace is owned by the government, but it's not run by the government. It's run by this other organization called INTES, which doesn't really matter. But there are 10 of these labs that are Office of Science labs, which if you're looking at a career in a national lab, you probably want to target one of these Office of Science labs. Argonne and Berkeley and Oak Ridge are all good national labs that do a lot of computing research. And then there are 3 National Nuclear Security Administration or NNSA labs. Sandia, where I work, is one of those, and the other 2 are Lawrence Livermore and Los Alamos. And you can learn more about those national labs at this website here. So a little bit about Sandia National Labs. We have campuses in both Albuquerque, New Mexico, and in Livermore, California. The bigger campus by far is in Albuquerque. I think the bulk of our employees are in Albuquerque, but we do have a smaller campus in Livermore, California. As of 2019, we had about 14,000 employees. I think at this point that's grown to at least 15,000. Our origins are in the Manhattan Project, which was the project that developed the first nuclear weapons that were used in World War II. So the main gist of the national labs of Sandia National Lab is nuclear weapons research. So our job is to keep the nuclear stockpile safe and secure and reliable to support nuclear deterrence. There's this phrase that gets thrown around at Sandia called always and never. We hope that we never have to use these weapons, and we hope that they would never detonate if we don't want them to. But if the president says to use one of these weapons, we would still want them to work. Sandia Labs in particular develops the non-nuclear components of nuclear weapons. Los Alamos and Lawrence Livermore Labs develop the nuclear components. And there's updating of these nuclear components, non-nuclear components for the weapons and extreme environments testing. So the really cool picture you see on the right, which we'll probably see in lots of Sandia advertisements, is a machine that allows the scientists at the lab to study different materials sciences. And they're saying what would happen to these materials under the conditions that might be produced by the detonation of a nuclear weapon. Now, even though the main focus is nuclear weapons, there are many, many, many other areas of research at Sandia National Labs. So they've done work in biological and chemical threat reduction. They've done recent research in COVID-19 research and antiviral countermeasures, in remote sensing, which is basically trying to figure out what sorts of data our satellites and other remote sensors can pick up, counterterrorism, cybersecurity, and microelectronics. So this picture at the right is a screenshot from the MESA facilities where they are fabricating computer chips. And Sandia has their own lab here where they make their own computer chips for their own devices. Sandia Labs, I think, was one of the first places to have a clean room. And I've actually toured this place in person. It's really cool because you see all the guys back here dressed up in their plastic suits and wearing hats. You can't have any dust in these rooms near those microelectronics. It's pretty interesting to watch. This is a screenshot from the virtual tour of that facility. There are lots of other virtual tours online of different facilities at Sandia, and you can find those at this website here. Now, my particular area of research is in the computing research. I'm not really on the nuclear sciences or nuclear weapons end of things right now. So I work with high performance computing, and we have people in our department looking at software and hardware architectures. We work with scalable software. So I mentioned the Trilinos library. COCOS is another linear algebra library that underlies that aims to be portable between different computer architectures. And there are plenty of physics and modeling libraries. We've got some people looking at neuromorphic computing, people looking at quantum computing, and also plenty of people looking at data science, machine learning, and artificial intelligence. And there at the bottom is a picture of, I think it's the top supercomputer in the United States right now, called Summit. At one point, it was the top supercomputer in the world, but that's been overtaken, I think, by Fugaku. But Summit is housed at Oak Ridge National Laboratory, and it's one of the computers that I get to use to perform my research. Okay, I think I mentioned, and I think it was mentioned in the flyer for this event, that I'm funded by the Exascale Computing Project. So what is that project? It's going to end in a few years, but basically this project was, how can we redevelop our software to run on exascale computers? So the first exascale computers in the United States are set to launch either at the end of this year or at the beginning of 2022. And two of them will be Aurora and Frontier, as shown in the pictures at the bottom. So the fastest computers today are on the order of petascale, or 10 to the 15 operations per second. And our new goal is to get to exascale, or 10 to the 18 computing operations per second. So like I said, we're writing new software that will take advantage of these new supercomputers. I talked earlier about CPUs versus GPUs. Computers such as Summit get 97% of their computing power from the GPUs. So you've got to write code specially to run on those GPUs. Otherwise, you're not taking advantage of 97% of the computing power of the supercomputer. So why did I choose a job at a national lab? So national labs, you can kind of think of them as a midway point between academia and industry. So there's no day-to-day teaching component as there is in academia. And you don't have quite as much freedom in your research area as in academia. Of course, you can still apply for your own grants. And in some national labs, you have to apply for your own grants. But other times in Sandia, you have projects where, you know, this is the project that needs to be funded to work on our lab's mission, and we need you to work on it. So you get a little bit less choice of what to work on than you would in academia, but you probably get more choice than you would in industry. Of course, in industry, you don't have to find grants and seek out your own funding. So it's kind of a middle ground between academia and industry. I do enjoy spending more time in technical research as opposed to teaching. I think teaching is valuable, and I wanted to do it well when I was teaching. But, you know, I came into grad school thinking I would go off and be a teacher at a small liberal arts college. And then I started teaching and I realized, I could take it or leave it. And teaching just isn't really the thing that I love. So I'm enjoying spending more time in technical research at a national lab. I really like learning to play with new codes and with big computers. That's one of the exciting parts of my job. I enjoy getting to work on real life problems. So one of the things that kind of annoyed me being in academia was that, my advisor had done some really great work on some really cool algorithms and published a paper on it. And then, we talk about all these linear systems that need to be solved from these great big physics problems, but nobody's using his better algorithm. And that was kind of disappointing to me. If I'm going to be working on better algorithms, I'd like somebody to actually use the algorithms rather than just publish a paper and that's the end. So that's one of the things that drew me to a national lab, is that I get to work on real life problems that people actually want to solve. And I get to write software that hopefully people are actually going to use. I enjoy being surrounded by experts in many different areas. So as I listed before, my whole department has experts in quantum computing, neuromorphic computing, all sorts of different areas of computer science and mathematics. And there are always new people to learn from. Okay, so what steps did I take to get me to a national lab? I would say be really proactive about finding conferences to participate in, research experiences for undergraduates if you're still an undergraduate, summer programs, etc., and be brave and go participate. And I know that that's changed a lot during COVID. In some sense, that's closed off a lot of opportunities because we can't go many places in person right now. But then in other ways, it's opened up a lot of opportunities because I found a lot of conferences that are virtual that I wouldn't have been able to go to in person, but I've been able to attend them virtually, and that's been really great. But my first steps toward a national lab came with attending conferences. My first step toward grad school came in finding an REU that I did over the summer after my junior year. And these programs are really important. Often it's more about who you know and what connections you can find rather than what technical skills you know. Those people connections are super important. Be proactive about learning computing skills outside of the standard math curriculum. So I love proofs. I hope you love proofs too. Proofs are great. But if you're going to work outside of academia, you're going to need to do things that aren't proofs. And the more computing skills you learn, the better. And I remember spending some time on different online courses in graduate school. For example, I was taking a course on Udacity's operating systems, which was one of the things I wish I had gotten to in undergrad and then I didn't. And I remember my advisor saying, I don't know if you're ever going to use that. But let me tell you, every single computing course I have ever taken, the skills that I've learned have come up somewhere. And I have definitely used all the things I learned in that operating systems course in real life. And I'm still learning. Get an internship. So I have basically 3 suggestions on how do you get an internship. And the summer that I got my first internship at Sandia, so I came as an intern in the summer after my 3rd year of graduate school in 2017. And that summer I applied to several internships and I was offered 3. And here are the 3 ways that I was offered an internship. One of them was just by putting in applications. So I had put in an application. A guy from Lawrence Livermore contacted me and he said, hey, I saw in your application you work with Krylov Solvers. We're trying to do something with actually multi-precision Krylov Solvers, which I ironically ended up working on later. And he met me at the first conference I had gone to and interviewed me. And I had an offer of an internship just by putting an application into the pool. But I will say, of all the applications that I put into different pools, that was the only one that got a bite. I got another internship offer from a friend's brother who emailed my resume to another friend who worked for an industry company that did something with self-driving cars. And she called me up and said, your resume looks good. We do things with linear algebra. You could have an internship here. But the internship at Sandia that I finally ended up taking actually came from a cold email. So this isn't your typical getting an internship advice, but sometimes it works. I happened to be reading the thesis of Heidi Thornquist because it was really similar to my thesis work. I was working on polynomial preconditioning for linear solvers, and she had done it for eigenvalue problems. So I found her email on Sandia's website, and I sent her a cold email out of the blue, never met her before for anything. And I said, hi, I'm a grad student at Baylor. I work on Krylov Solvers. I've been reading your thesis. Do you want an intern for the summer? And she said, yes. And that led to my internship at Sandia. And that internship definitely led to my later job. So, don't send cold emails to 1,000 people, but if you've got a legitimate interest in somebody's research, absolutely send them a cold email, ask them about their research, tell them a little bit of your background, and see if they want an internship, because often it's those personal connections that can get your foot in the door. Finally, build and maintain relationships with other mathematicians. At conferences in your school, you never know when these other connections are going to come up. So specifically internships at Sandia, at what we call the Center for Computing Research. We have internships available for undergraduate and graduate students. And there's actually an opportunity to transition into being what's called a year-round intern after you've had a successful summer internship. So if you want something that probably pays better than your teaching stipend, and you could afford to spend maybe half your time doing research for Sandia, and usually if you're doing an internship for Sandia as a graduate student, they want to make sure that your research at Sandia overlaps with your thesis research. So that's also really useful. So the work that I did as a summer intern in 2017 actually turned into the first chapter of my thesis. Applications for summer internships are pretty competitive due to limited office space, and even more limited due to COVID-19. So for summer of 2021, we're having virtual internships. All of those slots are full at this point. Applications for the next summer for 2022 will be opening in the fall, sometime around September or October. I don't know, nobody knows at this point whether those 2022 internships will be virtual or in person. They're still waiting to determine that. But if you're interested in those internships, keep your eyes open around September, October. Feel free to email me and ask about that around September or October, and I can point you to the right link to apply for those. Knowledge of any sort of C++, parallel programming, or the Cocos library that I mentioned is a plus, but at the end of the day, try to gain all the computing skills you can. And again, feel free to contact me to learn more, and I'll post my email address at the end of this. So I said learn all the computer skills you can. Here are a few specific skills you can learn to get started. You can learn the Linux and Unix command line. So I don't know how many of you have had any programming experience outside of MATLAB at all, but my programming experience started in my undergraduate computer science minor. We were working in C++, and we used this lovely program called Visual Studios, where you hit buttons to compile your code and you hit buttons to run your code. And my current world of programming is a world that doesn't have any buttons. When you log onto a supercomputer, you get a terminal screen with a line of text, and you have to learn to work in Linux. So the Linux Unix command line is very useful to learn, and udacity.com has some great free courses on learning the Linux command line. Learn Git and GitHub. Those are repositories for contributing to open source code projects. And again, Udacity, Coursera, many other places have some excellent free courses on this. Along with working on the command line, learn to use a command line text editor if you want to learn to get into supercomputing. So the two competing primary editors that people use are Vim and Emacs. I like to use Vim, and for that, one of my favorite learning tools is Vim Adventures. I'm not sure about the best place for learning Emacs, but I'm sure there are some great tutorials on Emacs out there as well. Learn to build a simple program at the command line. Oh, and this should really be 2 bullets. You could also learn to work in an existing code base. Working with a giant project like Trillinos is very, very different than working with, say, research code in MATLAB, and so on and so forth. So one summer opportunity you might look for this, if you have some coding experience, is called Google Summer of Code. And that's where they hire students to work full-time for the summer on an open source coding project. And I haven't participated in that program, but it looks very good, and that would be a great opportunity to build out your coding skills for sure. You can learn the basics of MPI and OpenMP. Those are both APIs for doing parallel programming. So MPI stands for Message Passing Interface. It helps you divide up your problem between multiple computers and organize how messages are going to be passed between those different computers. OpenMP is a similar program, but at least with OpenMP, you have processes that are all sharing a bank of memory. And for those and other ideas in parallel computing, there is the Exceed program. And their workshops used to be all in person, but because of COVID, their workshops have become virtual. And so they have free online workshops that will teach you how to code with MPI and OpenMP. And you need some C or C++ or Fortran coding skills before you attack that. So if you want to get into that area, I would make sure you have the basics of C or C++ or Fortran. Cocos tutorials. This is something specific to Sandia, but Cocos is a really good linear algebra library that's portable to different architectures. And if you know some C or C++, it's a great place to start with some parallel programming. And they have a whole lecture series that you can find at this link here, and lots of practice exercises for their tutorials. And other good resources, if you want to learn about high performance computing, there's the Argonne training program on extreme scale computing, which you can apply to participate in person if you are still a student or a postdoc, or they have many of their lectures posted on their YouTube channel listed here, which I have found really useful. And a few of my other favorite resources as a math grad student and so on. If you're a math grad student and you haven't checked out A Mathematician's Survival Guide, I highly recommend that, especially if you're thinking of going into academia. It gives a really good outline of the process of getting through graduate school in mathematics. What is it like to write a thesis? How should you pick an advisor? So on and so forth. There's the Learning How to Learn course on Coursera, which was helpful for me really as a student in learning how does the brain work, how does the brain organize information and retain information. Gave me some really good tips in studying for my graduate courses, and also a lot of information that I later used in my teaching. Mindset, The New Psychology of Success, is one of my favorite books that helps with, we'll say, imposter syndrome. And Deep Work, Rules for Focused Success in a Distracted World, has also been one of my favorite books for productivity and scheduling as a graduate student. So that's what I have. Feel free to contact me at my email address, jloe@sandia.gov, if you have any further questions or if you want to know more about internships, and I'll be happy to take questions.
Thank you so much. I have a question. So for internship or the job, does it require a green card or citizenship? I think that's one of the barriers.
So it depends on what you're working in. At Sandia, there are many jobs that do require a security clearance, and for that you need to be a US citizen, but that's not true at all of the labs. So I know I have several friends who are foreign nationals who work at Lawrence Berkeley Lab or Argonne National Labs. For my particular department, we're kind of unusual in that many of our people don't have security clearances, and we do hire several foreign nationals. I think it has become harder to get a job there as a foreign national in the past couple of years than it was previously. I'm not quite sure what the status is now, but it is theoretically possible to get a job as a foreign national at Sandia as long as you're working in an area that doesn't require a clearance. So if you're doing open math or computer science research, that shouldn't require a clearance at this stage. It is theoretically possible, but when you start applying at Sandia for internships or talking with someone who you think might be a potential mentor, I would mention that right off the bat for sure, and make sure that they can help you get in the process of working for that. So I don't think it requires a green card. I don't know if that works on your student visa or what exactly. You do have to have the right type of visa. I don't know all the details of that.
That I know. I just checked some of the internship where it was mentioned that citizenship required. That's why I was asking. Yeah,
in my department, I don't think that citizenship is required, but it does take a bit longer to get through the application process for sure. And we have hired many foreign nationals in my department. So it is possible. It may be harder than it used to be, but it is certainly possible. And if you're looking at different national labs, so Berkeley and Argonne wouldn't have the same security requirements, it might be easier to get a position there.
Okay, I have another question. So the computer skill, you mentioned that it's good to have them, but how mandatory is for me, like I'm third year student, like what level of computing skill I should know just to apply for internship?
A lot of that depends on the person you're working with. So, you know, I might start there with finding a potential mentor and saying, do you have any projects I could work on? Because there are some places in my department where they need interns who are C++ whizzes, who have C++ skills far beyond what I have and know details of parallel computing and such and so forth. But I also know people such as one of my mentors, Eric Bowman. He likes to do a lot of work in graph algorithms, and he might be able to find an appropriate project that you could do with only MATLAB skills. Or maybe they could pair you with another intern and you could work on the algorithms piece and the other intern could work on the coding. It just really depends on the project and who you're working with. So I would try to start having conversations early with potential mentors about what coding skills you have and what projects might be a fit for you.
Okay, thank you. Does anyone else have questions? I think you pointed out every question in the slides and answered it. It was very organized.
Thank you.
Thank you so much for your generous time and the talk.
Thank you so much for having me.
It was really great discussion.
And again, feel free to contact me if you think of any questions later. jloe@sandia.gov.
Okay, I'll stop recording right now. If anyone has questions, they can ask later on also.